All right, guys. Welcome to the third TA of Cognitive Robotics. I re-uploaded the TA onto the website like an hour ago because I noticed a calculation mistake. So if you downloaded it earlier today or something, just make sure to re-download it. It's not crucial, but that's that. So I'm going to start off firstly by discussing a bit about the project. So as you guys know now, you guys can propose a topic for the project. We will choose three or four of the proposals that the whole class proposes, and we will move on from there. So a lot of people have been texting me about their ideas in private. They have a project, and I think that's really great. I'm happy to see enthusiasm like that. I want to kind of show you guys more the direction of what kind of projects are within the scope of the course. We're not going to be able to solve super crazy problems like, I don't know, like P equals NP, for example. But like we can do some nice basic stuff as part of the project. And since you guys will be in groups of up to 4, you can really go deeper into it. So the project that I did when I took this course last semester, I did a project on integrated task and motion planning for a Mars rover, for the exploration of a Mars rover. It's a very simplified problem. I did it in a group of 2. And basically what we did was we wrote a whole Python kind of script. You can see here that it's like majority Python, a little bit of PDDL. But what the script does is it kind of initializes, let's say, a map of Mars. Here is where the rover starts, it's a blue point. Here are a bunch of obstacles, the orange circles. And these green circles are goal zones. And our goal was to plan an efficient path that would go through all 3 goal zones and return to the base point. So we used methods from this class that we'll learn later on. So for example, probabilistic roadmap is a motion planning algorithm that we'll discuss, I think, after Hanukkah, if I'm not mistaken. And it begins by sampling a bunch of points in the free space, finding those points nearest neighbors, connecting them in a graph, we'll see in a second, creating a big graph, running an algorithm like Dijkstra for finding the shortest paths, to find paths between all the nodes of interest, simplifying it to a traveling salesman problem, which we'll actually solve today in class, and then running PDL to solve the traveling salesman problem. That was the first part of it, and so we can see an example of a final trajectory that the rover might take between all the points. And we also did a bit with another algorithm for motion planning called RRT, rapidly exploring random trees, where we're kind of looking for a way to have the rover move its arm so that it can grab a goal that's inside a cave. So we applied like very basic algorithms for motion planning so that it could do the motions it's doing. You can see that's not very optimal. There are optimal algorithms that we'll discuss in this course that would solve this problem a bit better. But that's like you can see it's a nice project. It's not insanely heavy. I'd say we worked on it a total of a month. In terms of man hours, I don't remember. Just to kind of ground the ideas that are relevant for the project. So this is if you want to do like simulation type stuff. So it could be sort of in the direction of these kinds of things. If you want to work with physical robots, that's going to be much more involved. But like, of course, we'll support you guys to do it. Just if you have ideas how you want to go about, I don't know, using the robots in real life for something interesting, then we will consider it and we'll try and make a nice project out of it. I'm going to create kind of a formal way for you guys to submit the project proposals. And like we'll have all proposals due probably early December. So you guys have time to think about ideas, discuss with your teammates, and then we can still have time before the end of the semester to actually work on it. That's that. And in terms of the homework, I'll create a way for you guys to add partners on Moodle, and then we'll release in the next week or so the first homework. So that's that in terms of the project. I think, did I record that? Yeah, I did record it. All right, good. So welcome to episode 3, the Plan-dalorian. So today we're going to actually start discussing our first real artificial intelligence algorithms. Sorry. Up until now, we've kind of just been looking at ways to represent these problems for some sort of black box AI solver. And now we're going to get some basic insight, not too deep, but some basic insight into how an AI solver might approach a classical planning problem. So first we can kind of build the idea of a state space. Also, for the record, for anybody who's you've done intro to AI, right? Has anybody else done intro to AI or any like artificial intelligence courses? If you're doing it right now, like this should be. I'm also taking it right now, actually. This is like we're going to cover right now just a bit of the first 3 weeks of that course as a nice intro to what we'll be doing in this course. So for those of you who are in the intro to AI course, you have already heard about state space and state space search. But what we'd like to do when we approach a classical planning problem, where we know the initial state, we know the goal state, we have deterministic actions, is we can kind of look at an initial state and start looking at which actions are applicable, propagate those actions, see the new states, and so on and so forth. And when we do that, we can start to build a state space, which is the space of all reachable states in our classical planning problem. So we kind of have 2 common ways to portray the state space. So we can use search trees, we can use state space graphs. State space graphs for large, for complex classical planning problems aren't super efficient to represent in memory. So we'd never really build them out like this. Search trees, you can build them while you go. Usually also won't represent the whole search tree in memory. These are 2 more or less equivalent ways to represent the state space. The only difference being that this is undirected, this is an undirected graph, and this is a directed graph. And usually when we're dealing with classical planning problems, a lot of those solvers will be looking at search trees when they want to solve their problems, mainly because it's fairly convenient to extend the tree as you go and only to store in memory the nodes and the branches that you need, rather than trying to represent the graph in some way. So there are 2 main approaches to say, look at a problem or start solving a problem with the search trees. So you can go from the initial state. We can use something called forward search. So we start looking at what's the next state that we can do, we can reach, what are the states after that, and so on, with the actions that are available for those states. When we go from the initial state, we go down and we try to look for the goal state. For example, here, that's forward search. And alternatively, we can start at the goal and look backwards in a backward search and see what actions could we have applied to reach the goal state, and we move backwards until we reach the initial state. So we didn't really discuss yet how we would choose kind of the path when we expand. So I said that we can go forward here, we look, and I've only looked at this kind of branch here, but I could have easily chosen this branch, extend it here, and maybe I would have found a solution, or maybe I would have hit a dead end. So this is where we come to search algorithms, which should be very familiar to those who have already done courses that teach search algorithms like BFS. But these algorithms kind of tell us, how do we approach looking through search tree? How do we choose which nodes to expand next? So for example, we have breadth first search, which is at each tier of the tree, we expand every node in that tree, in that tier, before we move on to the next tier. So we use a FIFO queue, a first in, first out. So every time we add so let's say I expand this node, and I added 2 nodes to my fringe. The fringe is the kind of the wait list, let's say, of the nodes that I want to explore. And so when I expand A, I add B and C to my fringe. And then before I move on, I will explore both B and C. Then once I do that, I expand both of them. And before moving any further, I will look at D, E, and F, and so on. I won't just take one path, I will explore all paths kind of at the same pace. Next is DFS. So if I, rather than spreading out evenly, I will attack one path more like kind of rapidly, like I'll only look at one branch. If that doesn't work, then I'll backtrack up and I will look at the next branch, and so on and so forth. And we have uniform cost search. So the other searches that we've looked at, just BFS and DFS, they don't check for the cost of committing an action. They just assume that the cost of every action is just 1. But sometimes if you want to move an object from place to place, there's obviously a cost such as the geometric distance between those places. And so we can assign costs to actions, and we can use uniform cost search to conduct our search. So we will look at the lowest cost path, lowest cost path at each point. So we'll expand nodes based on which ones are the least costly up to that point. So it's kind of similar to breadth research, but instead of looking at all nodes in a tier, it kind of looks at all nodes on a cost contour. So around the same cost level. So there's 3 properties of search algorithms that we care about and we want to consider when we apply them. So that's their complexity, their completeness, and their optimality. So in terms of explain each one. So complexity, so we want to know how much time would it take an algorithm to find a solution. And space-wise, we want to know how much memory do we need from our computer in order to actually conduct this search. In terms of completeness, so if there is a solution to our problem, is our algorithm guaranteed to find that solution? It doesn't have to be optimal, just is it guaranteed to find a solution? And optimality, is our algorithm guaranteed to find the optimal solution? So the best solution, lowest, whether it's lowest cost or least number of actions, depends on what you are looking for in that problem. So when looking at complexity, if we have a search tree, we can define a parameter called B, the branching factor. So if I look at a tree like this one, the branching factor from A will be 2 because it expands into 2 nodes. And for B it's 1, for C it's 2 because it's expanding again into 2 nodes. But we'll take B as usually as an average for the whole tree, rather than using 1 or 2. We can take an average over all the branching factors, or we can estimate it. We can also do a worst case. Just depends on what kind of analysis you want to run. And then we have another parameter called M. M is the depth of your search tree. So how many tiers does your tree have? So here we have 1, 2, 3, 4. We have 4 tiers. That's the deepest we can go in our tree. And so we can say that the size of a tree, the number of nodes in the tree, will usually can be approximated according to the formula of adding 1 plus b squared. 1 plus b squared, and so on. And it's on the order of b to the n. So if we want to look at what's the complexity of BFS, so BFS will stop once it gets to the shallowest solution. So for example, here, if G is my solution, then it would stop here. It wouldn't keep going to the last G. That would be the shallowest solution. And that means that the S would be 1, 2, 3, 3. So in terms of complexity, we see that BFS has a complexity on the order of B to the S, the branching factor, to the power of the depth of the shallowest solution. Same for its space complexity. Looking at DFS, so DFS, if it chooses the wrong branch, could hit the lowest branch, the deepest branch in our tree. So it could go all the way up to M. So it's going to have a M complexity of B to the M, and its space complexity is B times M, since it's only storing the nodes in the path that it's looking at and then siblings of those nodes, so that it can do backtracking. So it's not as harsh as BFS in terms of space complexity. Lastly, we have the complexity for uniform cost search. So if I define that the solution has a total cost of C, and the minimal cost for any of the edges will be epsilon, then we can have effective depth, C over E, and this will allow us to define the complexity of UCS, which is both time and space. It's order of B to the C over E epsilon. In terms of completeness, so BFS is complete. It will always find a solution no matter what, as long as the state space is finite. So most of these, in terms of completeness, will rely on the state space being finite. If you have infinite state space, you could just search it forever. In classical planning, we won't have infinite state spaces. They will almost always be finite. So BFS will always be complete. DFS, again, is complete as long as n is finite. And if I would have an infinite state space, I could limit it using some maximum depth that I'll call L. And this would be the, for whoever recognizes it, the DFS-L algorithm. And for UCS, again, assuming a finite condition, UCS will be complete. And in fact, UCS is optimal in terms of the cost. BFS is only optimal as long as you're not considering costs. So if you let the cost of every edge be 1, you're only counting the number of steps it takes to reach a solution, then BFS will be optimal. Otherwise, in terms of cost, BFS is not necessarily optimal. And DFS is certainly not optimal. It will just explore one path at a time. And if it finds a solution, for example, on the left side, and I have an optimal solution here, it'll just hit the solution that's leftmost. So it's not necessarily going to be the most optimal. Okay, so now moving on from what we call uninformed search. So we just discussed algorithms that have no clue where the goal is. They're only aware of the actions that are available and the cost of those actions. They're not informed at all about where the goal is. So now we can apply something called heuristic search. So if we want to approach algorithms a bit more intelligently, we want to conduct our search more in the direction, let's say, of the goal, we can use heuristics. So a heuristic will be an estimate of how far any state is from the goal. And so, for example, as a heuristic, let's say I want to travel from Haifa to Tel Aviv. I could use the distance between my location and Tel Aviv at any given moment to be that heuristic, that straight line distance. So if I have, so I can create an algorithm that will always try to minimize or maximize a heuristic depending on what it is, and that's called greedy search. So greedy search, at least in this case, maximizing the heuristic. So it'll always look for the largest heuristic values. Here it's 7, here's 12. 12 is bigger than 3, so it chooses 12. And 6 is bigger than 5, so it chooses 6. So you see that greedy will always go in the direction of either the highest heuristic or lowest heuristic, depending on what you've asked it to do. It's not necessarily optimal though. You see here that we're missing out on this huge weight value that it didn't explore because it was being greedy. To deal with this, so in this case we have it, our greedy algorithm still misses on the huge values. We can kind of intelligently merge the heuristic values that we had with the cost values that we saw, for example, in UCS. So we can actually consider both what's the cost of each action in the path that we want, and what's the heuristic value in the nodes in that path. So what comes out of this? We get an algorithm called A-star. So A-star is, of course, one of the most prevalent search algorithms still used today. I think it was developed in the 60s. I mentioned last week that it was developed for the Shaky project, the first cognitive robot at Stanford. So what A-star search does is it's minimizing this sum, which is the cost plus the heuristic. So it considers both of those things when it conducts its search through a graph. Now the limit on A-star is that this heuristic has to have a property called admissibility. So any heuristic that I want to use, it cannot overestimate the distance to the goal. It always has to be optimistic and underestimate the distance. So for example, let's say that, again, I'm going from Haifa to Tel Aviv. And realistically, the road from Haifa to Tel Aviv is probably something like this. So if I want to make a heuristic that will allow me at any point to estimate my distance from Tel Aviv, I could use a straight line distance. And from clear geometry, I know that this distance, which I'll call hx, is always smaller than the true cost of taking this path, which is, let's say, h star x. So this heuristic is admissible because it always underestimates how far we really are from Tel Aviv in terms of the path that we want to take. So A star is both complete and optimal. So that's quite nice, assuming we have a finite state space. The only drawback that we have with A star is that it is quite complex in terms of space. So it'll have to store all the nodes in the tree, B to the M nodes, order of B to the M nodes. And time-wise, it's still also complex at the same complexity. And this is because I think you can see here, it's going to measure the cost plus heuristic for every single node in the graph, and then it'll choose the shortest path based on whichever one minimizes that function. So even though it's quite complex, this is still one of the most widely used search algorithms, and actually in classical planning, they use it in quite a large variety of search algorithms. So now we've done a nice little intro. So now how does this actually relate to our course? So when we conduct our state space search, we can apply, of course, heuristics to it to speed up the search process and kind of get closer to the goal. If you try and think about it, it seems a bit complex to think what would be the heuristic for a task planning problem. It's hard to kind of measure your distance from a goal when you have a set of predicates and a set of actions, and you're trying to, I don't know. For me, at least, it's hard to conceptualize what the distance of any given state would be from the goal state in a Boolean problem. Luckily, there are people who are much smarter than me. They've come up with quite a few interesting ways to approach this. So, for example, one of those ways is something called relaxation. So, I think did you cover this in the lecture this week? Relaxation and heuristics? No, right? No. So it'll be next week. So what we can do is we can take our task planning problem, our classical planning problem, and we can kind of relax it, massage it into a bit of an easier problem to solve. So for example, something that you'll see next week in your class, in lecture, is that one way to relax a classical planning problem is to remove all the negative preconditions, negative effects. So if I have an action that has an effect that's negative, so if it says not at, for example, it'll just delete all those nots, and it'll solve that problem. And you'll see more of how that really works before next week in lecture. But if we have a relaxed problem like that, what we can do is we can calculate the cost according to some cost metric in that relaxed plan, and that will become our heuristic. So the cost of a solution in the relaxed problem will serve as a heuristic in the original problem. So I put here a few examples of planners that do this. I can't really go in depth too much into them in this class, but I attached a bunch of videos and their papers and stuff. So if you click on these links, there's plenty of resources and stuff so you can learn more about these algorithms. But for example, we have heuristic search planner, which, as I said, what it does is it kind of ignores the not statements in the effects of actions, and it'll solve those relaxed problems and use that as a heuristic. Then we have fast forward, which is based on HSP, but it uses a bit more clever tricks to kind of optimize how it goes about solving a problem, and it's much more efficient. And then there's fast downward, which is the most recent here, and it's one of the most efficient, at least in this list, in terms of heuristic search algorithms. I think Erez will explain fast forward next week in the lecture, and fast downward, I'm not sure if he will, but it does rely on something called causal graphs, which you did learn about at this week's lecture. If you need to go over it, you have the notes there. But basically, it does something similar to the other algorithms, but its heuristic is now based on something called causal graphs. And we will apply it later on next week's tutorial. We're going to use a Python library called the Unified Planning Framework. So this is a very convenient library. Unified Planning Framework. Actually, can you guys see this? Should I zoom in more?
Yeah.
So it's Shift plus, like Control plus. Control plus. Is that better?
Yeah.
All right. So yeah, right. Unified Planning Framework. So this is a Python library that allows us to easily build classical planning problems in PDL, but using Python. So instead of having to write a PDL file, we can just write some commands in Python, and it'll spit out the file for us automatically. This is much easier for integration when you're going to work with Python. I used it extensively in my project last semester, and I found it quite useful. It still has its limitations. It's very new. They started it in 2020, I think. It's some organization related to the EU, but it's a very useful library, and we'll learn more about it next week. But anyways, it's integrated with this planner that's one of the most efficient, called Fast Downward, and we'll see how to use it next week. Aside from state space search, so state space search has its problems. It's a bit too complex because of how we represent our problem. So there are some other methods that have been used since the beginning of the expansion of classical planning as its own field. So there's plan space planning, the planning graphs, which you'll discuss I think a bit in the lectures. Planning graphs are one of the most efficient ways to actually solve classical planning problems. So using an algorithm called GraphPlan, it manages to kind of get around the difficulties of state space search. We also have partial order planning and planning and satisfiability. So this one's an interesting one because they take planning problems and turn them into Boolean satisfiability problems. So if you know stat problems like 3-set and so on, so it'll take a classical planning problem and kind of morph it into one of those, and then use some well-known stat solvers to just solve that problem. It's efficient sometimes. So they showed in the beginning that it was better than heuristic search, and then heuristic search was better, and then it's kind of a flip-flop over the decades between which method's better. But everything has its own benefits. And I've attached here a YouTube playlist from the University of Edinburgh. They cover a lot of the stuff I just talked about in much more depth. So a lot of the algorithms like graph plan, like planning graphs and so on. So if you guys are interested in learning more about that, it's a great resource. I've watched a lot of those videos, so I can attest to it. So now we've done our basic intro, we've done a little bit of theory. Now let's see how we actually can interpret the problems that we want to solve using these methods. And again, we'll solve them using PDDL as we did last week. So I'm sure most of you know the Tower of Hanoi. So we have an n number of disks sitting on one peg, and we want to move them to another peg. Our limitations are that we have disks of decreasing diameter. We can only stack smaller disks on top of bigger disks. And the disk has to be clear on top. There can't be any disks on top of it in order for us to move it to another peg or another disk. So this is actually a benchmark problem in classical planning. Almost every planning competition that exists, they'll test the algorithms that they run on Tower of Hanoi, for example. So this is just the n = 2 case. So right now we're going to write it out in PDL. Before we do that, let's try and think together. I want to be able to try and make it a bit interactive if you guys want. Let's try and think what might be relevant for us to include in our PDDL representation. So let's start with the domain file. So already I'll just say we don't need types here. But what objects should we represent here? What are the relevant objects that we'll create in the domain file? The disks and location, or the pegs. Yeah. So we don't need to do typing here. I think it complicates it a bit every week. In this problem, and like you kind of get intuition for when you need to represent the object, like when you need to create new types for new objects. But in this case, we don't need to. We'll just declare these objects in the problem file. So we don't really need to touch objects in the domain file. And now let's think of what predicates do we need. So what Boolean statements do we want to ask about the state of our puzzle? On. Bigger than.
What?
Is on bigger than. And there should be one more. Really?
Location, which one?
That's like on. You can get them both at the same time. So we have on, we have bigger than. And what's the other condition that we have? That we can't move a disk if it's not clear. So we also want to check if there's a disk on top of another disk. So whereas we want to check with one predicate if this is on this, we also need to check if there's anything at all on this. Those are kind of somewhat equivalent if you'd want to do a search through all the objects in the space and say, are any of these on the disk? But we'll just compact it into one predicate that's just called clear. So we start, and like we said, we have on xy, clear is the disk clear, and smaller is b smaller than a. So I did it this way, so the disk b should be smaller than disk or peg a. And we'll see, like, one of the reasons we didn't define pegs and disks as separate objects is that here it's convenient to describe on applying to all of them. So a disk can be on a peg and a disk can be on a disk. And a disk can be smaller than a peg and a disk can be smaller than a disk. So it's just easier not to do any typing here. And clear, of course, applies both to disks and pegs. So again, like typing wouldn't have made things easier for us. Okay. Here I accidentally deleted part of the action. But let's think, what's the action that we need in this space, in this problem? Move. So what are the preconditions that we might need for move? Clear. So the disk we want to move has to be clear.
Clear from, clear to.
Clear from and clear to, exactly. And what else? Let's think. So I'll give you the parameters. So the parameter for move would be the disk that we want to move, the original location, and the final location. So we've already considered that both the final location and the disk have to be clear. What else? Sort of with the order. We already said clear. What else?
Not the same location.
It has to be at the okay. So at the disk has to be at the from location. So if I'm going to specify disk from to, I have to make sure that disk is actually at from. So that's the third one. And the last one relates to the order. I have to check that the disk that I want to move is smaller than the location that I want to move to. So it has to be smaller. So I'll open the file because I didn't put the whole
Can you
thing.
repeat the last one?
Yeah, so you see that we have the clear is like you said, and we have smaller. So if I want to move a disk to a location, it has to be smaller than that location. So a disk has to be smaller than a disk that it wants to sit on top of. So if I want to move it to another disk, it has to be smaller than that disk. And we'll see, like with the pegs, we kind of also need to define them as smaller. No, you can, like the limitation of the problem in the problem definition is that you can only stack a disk on a bigger disk or on a peg. So we'll pretend like the pegs are bigger than the disks for the sake of this problem. So you can only stack a disk on a bigger disk or on a peg. So again, here's the action. Here's the parameters. As we said, disk and location that wants to be moved to has to be clear. Disk has to be smaller than its location to be moved to. And the disk should be on the original location. And I'll just tell you what the effects are. So as you could guess, the disk is now on the to location. The from location is clear because we can move the disk. The to location is no longer clear because the disk sits on it. And the disk is not on the original location anymore. So that's the only action we need in this problem. And now I'll just show you what the problem file is, or I'll go through it. So of course we instantiate our objects. So we have two disks in this case. We'll just do n = 2 for now. We have the two disks and we have the 3 pegs. In the initial state, I'll say that disk 1 is on disk 2 and disk 2 is on the first peg. So I'll say that the first disk, the small disk, is clear. The other 2 pegs are clear. And then I define the smaller relations between all the disks and all the pegs. So the pegs are, of course, bigger than the disks, let's say, so that I can always move a disk to a peg. And I, of course, have to add that disk 1 is smaller than disk 2. So I just wrote it backwards. That disk 1 will be smaller than disk 2. And my goal state is that I want, again, this one to be on disk 2, but this time I want disk 2 to be on peg 3. So I want them both to be on the third peg. And that gives me this problem file. This problem file. So before we run that, we can kind of get an intuition because it's not too much of a complex problem. We can look at the state space representations for the tower of the problem. So if I want to do a search tree, I can do it like this, and a state space graph look like this. So here I've done something called pruning. So I didn't show any repeat states. So if I look at a branch, look at a path, I didn't repeat any states that are in that path already. So that's a method called cycle checking. Where I prune any branches where I'm repeating a state I've already visited only in that path. So if I have this state, I go down here, for example, I'm not going to put the green disk back on the red state, just because I prune that state off because it's a repeat, and we'll assume that kind of independence between states. And in the state space graph, I can represent everything. So I have an undirected graph, so you can see I could move backwards this way if I wanted to, but I want to wait for my solution. And we see that for both cases, we have 3 steps to do. So they predicted, well, the calculation is that it's 2n minus 1 solution steps for every tower of the node problem, where n is the number of disks. So in this case, we have 2 disks. So 2 to the 2 minus 1 is 3. And as you see here, there's 1, 2, 3 steps to get to the solution. Same in the state space graph. So here we only have to explore 14 nodes. So it's on the order, say I use BFS, it's on the order of the branching factor to the length of the shortest, the depth of the shallow solution. So in this case, again, it's 3. And I'll assume a branching factor. You see here that there's like 2 nodes expanded from each node. There can be more, but here I'll just assume it's 2. So that means that I have on the order of 8 nodes to explore in BFS, and in reality, I explored here 14. Order being like 10, 100, 1,000, and so on. So 8 and 14 are like kind of on the same, say, order. Just one thing to note, so I'm sure many of you already know this with the Tower of Hanoi, but one of the more interesting cases for Tower of Hanoi is when n equals 64. I think there was an Indian legend about a Brahma who wanted to solve the Tower of Hanoi with n equals 64. So it turns out that there are a very, very, very large amount of steps to take for the optimal solution for the Tower of Hanoi with 64 disks. And if you wanted to move one disk every second, it would take you, I think, 42 times the lifetime of the entire universe to actually finish the problem. So you can imagine that if I wanted to apply BFS to this state space for the n equals 64 case, this is a huge, huge state space. So this is a state space on the order of 2 to the 2 to the 64. So 2 to the something 10 times 10 to the 19th power, which is an absurdly large number that no computer in the universe could ever hold. So BFS would be super inefficient for a large state space like that. So that aside, looking back at a PDDL, so if I open the problem file, I can run it using PDDL, and it'll find a path. Is it less than 1 second? Here it was 1 point something seconds. Usually it's less than 1 second, but it found exactly the path as we'd expect. And I also included the Tower of Hanoi for three disks. Again, if I run that, yeah, give me a plan in less than a second. It uses a method here. Here it uses BFS, actually. So by default, it starts with iterated width, which is an algorithm we discussed today. But for example, in the n equals 2 case, it solved it with iterative width. In the n equals 3 case, iterative width, I think, wasn't successful, if I'm not mistaken. Or maybe went, yeah. So it did try an IW search, it didn't work. So now then it went on to a BFS search. So BFS we actually discussed. And luckily our state space isn't so huge. And so we were able to use BFS to solve the n equals 3 case. And you see there's 7 moves. 2 to the 3 minus 1 is 8 minus 1 is 7. So 7 steps, as we'd expect, we got the exact solution. X out of this. So that was just, again, another little refresh of how to use PDDL. Now we're going to do in this part of the tutorial, since we have 10 minutes left. Luckily, I'm very good at timing things somehow, so it's worked out nice. But I want you guys to actually start writing PDDL files yourselves, because I think there's value to actually getting your hands on with any programming type of things. So what we're going to do in the next 10 minutes is I'm presenting to you this problem called the traveling Jedi problem, which is just the traveling salesman problem, but I didn't add any weights. So let me zoom out just a little bit. So this is a traveling Jedi problem that I've taken this graphic from the internet and added the graph onto it. Let's say Luke starts out on Tatooine, his home planet, and he's with his friends in the Millennium Falcon, and they want to take a road trip with the boys throughout the galaxy. And they want to visit all these planets exactly one time and then return to Tatooine. They don't want to repeat any visits because that would be inefficient. They don't want to waste any fuel. And so their goal is to start at Tatooine, go once again to every node in this graph, to every planet in the galaxy, and then return home to Tatooine. So this is exactly the traveling salesman problem. Here we don't add any weights, so we just are working by, let's say, cost equals 1. So every path has the same cost, and we just want to know if there's a path that goes to all of them once. We don't care if it's, the optimality will be defined by the number of steps we take. As you can imagine, that's 7. Like there are 7 planets here. They're not all planets, but 1, 2, 3, 4, 5, 6, 7. So there's 7 bodies here, 7 nodes to visit, kind of, including Tatooine because we visit it at the end. There are 7 nodes, so we can imagine that the maximum depth of our tree will be 7. But there's not really many. There's no way for us to visit 8 planets because we visited all 7 already. So that's the problem. Just a little nerd digression. So a lot of people think that they went to Endor in the movies. They didn't. They went to the moon of Endor. Endor is a gas giant. If you went to Endor, you would suffocate and not have a great time. Of course, they didn't go to Alderaan because Alderaan exploded, and you wouldn't really want to go to vacation on an exploded planet. So they're going to pass through the Death Star. let's imagine that's a vacation spot for the sake of this problem. Just for now. So this is the problem. What I'd like you guys to do is open up your computers, try and write the PDDL files, the domain in the problem file. That might represent this problem, and that would that we can use to solve using a PDDL solver. So you can start now, and then also if we have time, I'd like you guys to try and start drawing the search tree. So try and look at what's the search tree going to look like for this kind of problem. I promise it's not too big. It's 43 nodes. I've already drawn it, which is for your sake, and you can see what kind of algorithms might be efficient on this kind of search tree. Yeah, so go for it. I'll walk around if you guys want help with anything. But this will be until the end of class, and then at the end in like 10 minutes, we'll just discuss the solution. Does everybody know how to run PDDL? Okay, so if you have the VS Code extension, you go to the problem file. You right-click on the problem file, like in the tab, and then you click here, run the planner, and then just choose defaults, and it'll run the problem. And if you're using the online, there's of course the website online that you can use, planning.domains, I think. There you just run it, like you just load it. Okay. Okay.
הספורט, פשוט יש לך workspace, כאילו חדש, תעבוד משם. נכנס כל פייל, פשוט open folder, אז צריך את המקייה של התרגול. לא, יש לי איזה מעניין, כן, אבל איך זה, כאילו, לא ב... אז לא בטח את ה... שזה איך פשוט צריך רק כאילו, אתה רואה כאילו, לא, זה cancel. open file, אז החוצה. עכשיו אתה יכול קצת פה קובץ חדש, יש לך עכשיו זה מה שאתה רוצה, דרפמין, זה מה שאתה רוצה, זה יוסף. כן, אז הוא מה קורה שזה פיזיה, ועכשיו אתה יכול להתחיל לבדוק את השרצון. יש לי פתיאן, אתה בן שהוא לומד, אבל יש לו... כל זה עתיק בטאור בנוי. בטאור בנוי. יש פה... זה לא כמו פייטל מסוים, זה לא שכם בספייס או משהו, רק זה ספייס. ואתה יודע שנראה לך לא. לכם הולך טוב. אתה צריך לסור שבפרופיל, אתה צריך רק להזכיר את השם של דומיין. זה בשורה, תראה את זה בפרופיל שיש לו. Security trigger different files. So if you want to solve the PL, go into this and you need to add the all files. Yeah, you see the two files. So our context is on. So how should I do the definition? So you first you will series of additional values. Okay. Give location solve. It'll ask me to change the domain. Good. The function write the video פשוט on ואחד. לא, אבל למה אחד? אבל יש לי כאילו 7 משתנים. כאילו, הייתי 1 לפי 7, לא? כן, 7 משתנים, אבל אני משתנים מה... זהו, זה אולי לא משתנים.
يقدر الصوت automatic يقدر Python or whatever شو تقدر يقول لك عندي Python pause بتساوي أنا لو مش
Tornato un certo che ci fa quello che fattivo, invece che sera da mai diciamo Asphonics anche che ci sono con attività quanta what pretty good small setup shit I make that okay that's okay lo esattamente strumenti sono
adesso si manca essere ce l'ha that's the negative conditions should let them I'll say this in English. So negative preconditions. So if I have any precondition that has not in the precondition for an action, some solvers can solve that kind of problem. Like they're very vanilla versions of problems. So there's in the requirements in the domain file, you add a requirements called negative dash preconditions, and it'll allow you to use. It'll force the PDL solver to use negative preconditions, or it'll choose an algorithm that can use negative. I suppose che io forse ce l'abbiamo hai indicato per esatto, lascio da chiaro, anche il buono di questa scelta as I make the planet consume sport ma chi la scelta pochi lo attacchi riescono mai che allora che vada che che lo dai là che c'è poi dice noi è clear when actually I'm discussing the emission ma on I'm this as a chief quindi hai fatto la mappa Okay, so since we're running out of time, I'll show you guys the solution. You're free to work on it if you don't. I just don't want you guys to miss out. So looking at my domain file. So again, as I said, I included negative preconditions, like I said. So my predicates are at is loop at a planet, adjacent is planet 1, adjacent to planet 2. Are they near each other? Like, is there an edge connecting them? And visited. So this is what we were just talking about. So have I visited this planet? Yes or no? So I only need one variable, which is the planet itself. If I look at the action, so I only really can move between 2 planets. So my parameters are just those 2 planets. And the preconditions that I need are I have to be at the original planet, the planets have to be adjacent, and I haven't visited the planet that I want to go to. And the effects are that now I'm at the new planet, I'm not at the original planet, and I have visited the planet that I've just arrived to. And then my problem file. So this is what we're saying. It's not so nice to represent this just yet in basic PDL. Let me hide this. But we have all the objects, all the planets, all 7 planet object things. And my initial state, I have to declare that all these things are adjacent to each other in both directions. So I did adjacent L1, L2. but it's agnostic to the fact that L2 and L1 flipped is the same thing. So here I have to do both directions. So for example, Tatooine is adjacent to Coruscant and Coruscant is adjacent to Tatooine. I could do it more efficiently, but this is just how I did it here. And of course, I'm at Tatooine. So I start here. My goal will be to be back at Tatooine. And for all objects, I want to have visited an object. So here I used the universal quantifier for all. And I've said for all objects, I want to have visited them. I could have written it out like one after the other, visit this, visit this, visit this, but here it's just a way to shorten it. And if I run it in PDL, if I run it in PDL, I get my nice little plan, which is 7 steps as we expected. And that'll be starting at Tatooine, I fly to Hoth. From Hoth, I go to Naboo, Naboo to Dagobah, Dagobah to the moon, moon to Death Star to Coruscant, and back to Tatooine. There are 2 paths here, so I'll show you quickly the search tree. Where if I put it here, here. So this is the search tree of this problem. See if I can move this out of here. I have no idea how to hide this thing. I'll leave it there. This is a search tree of my problem. So if I start at Tatooine, I can go to all these states. The only thing I did here was I didn't specify when we terminate at Tatooine early. So there are some states where I'll reach Tatooine early, but I have to go there. So I ignored all those states. But here we see all the red states. These are what we call leaves. So they're nodes in a tree that don't have any children. There's nothing going out for them. So these are all not solutions. These paths don't give solutions. And we have 2 solutions here in our tree. You'll notice that they're actually the same. They're exactly the same path, just flipped. So here we start at Coruscant, and here we start at Hoth, and it's exactly the same path, just reversed. So this is our search tree. There's 43 nodes, 42, I remember, in the search tree. So I think the complexity for BFS, it would have to explore 128 different nodes, and here it's 40. So not too big. And we can imagine if you guys would want to do it as an exercise, you could try to run DFS on this, run BFS. You don't really need to run UCS. Let's say BFS and DFS, you could look at how it would work, and BFS would look at each tier by tier until it reached this level after going through 7 tiers. And DFS will just, if you go left to right, it'll just choose this one automatically, the ones that reaches there. So that's it for today. Next time, if we're doing interactive stuff like this, I'll try and plan more time a bit for it. But this is kind of similar to what stuff we'll do on the homework. So, and you can apply this, of course, to the project. But that's just what I wanted to cover today. Thank you guys for coming. And yeah, have a nice week.
I got to set it up.